It's called material extrusion. So basically, you have one strip of material like a filament, a feedstock material, and it needs to be filled into 2D space to form layers. So each layer is formed by depositing the material, the filament, and to create this layer together with the support structures. So just one thing I would like to emphasize here, you have two spools of materials. So both the building materials and the support materials. So they are two separate things. So basically, the support material is cheaper than the building material for sure, because afterward we need to eliminate the support structures and to recycle the support structure material. And in order to deposit the material, so the two filament will go through so-called extrusion head, where we can heat up the material, yeah, how can I say, turn it from the solid form to some kind of not really a liquid form, but it melts. It melts and can be deposited onto the surface of the how can I say, building plate or onto the previous layers. So we have
here the
two
two
extrusion
extrusion
noses
noses
where we can
where we
deposit the
can deposit the
material
material
through
through
and to the surface of the building plate or the previous layer of the part. And depending on the definition of the scanning vector, so you see that the extrusion head can move along X and Y directions. And after depositing completely the one layer, so we can have the Z movement created by the piston below the building substrate. Yes, the building substrate or building plate or building platform, whatever you call. Yes, and continue to deposit the upcoming layer, upcoming layers. Yeah, whatever. And the process is repeated until we have built up the whole 3D physical part. And the commercialized technologies which are available in the market, on the market at the moment, is a fused deposition modeling, or in or we also have the other technologies called fused filament fabrication. So the principle are similar to each others. And in terms of the field deposition modeling process, or we can simply call the field deposition model, the material, the input material can be the thermoplastic material, but other material can also be used. For example, thermoset, elastomer, polymetric composite, concrete, and others. But the common material that can be used for fused deposition modeling is thermoplastic polymer filament. And as I already mentioned to you, the filament, the polymeric filament, is fed through the extrusion nozzle. Of course, it passes through the hole of the nozzle after heating to a certain temperature to turn it to the some kind of melt form or molten material, and extrude through the nozzle gate, let's say. And then depending on the movement of the extrusion head, so we can have the part, deposition part, yeah? And it's been deposit line by line, layer by layer, in order to form the 3D object. And since this is the additive manufacturing technologies and the properties of synthesized material after the fabrication process strongly anisotropically. So it means that the properties in different directions will be different. So you can easily see the difference between, let's say, the horizontal direction and vertical directions. So they will absolutely have different properties. Yes, if you compare the strength, so the strength will be different. The hardness will behave similarly as well. I mean differently in different direction. This technology is widely spread and had the lowest cost comparing to the other additive manufacturing technologies. Yes, and last time I showed you about the video clip highlighting the technologies, especially the working principle of this technology. Yeah. And this is the first one among the seven, let's say, additive manufacturing technologies. But I would like to note here that uh, even if we have the seven category of additive manufacturing, but in each category or in each group, we have several, uh, let's say, sub category class, let's say, or subclass. So we will have several, let's say, commercial technologies which have different names, but it can be belong to one group. For example, here, material extrusion, you have the two commercialized technologies belong to this material extrusion group called fusion deposition modeling or fused filament fabrication. And the principle should be similar to what I have described on this slide here, graphically, yeah, because it's quite easier for you to easy for you to observe or to understand the working principle of the technologies via the pictures rather than showing you a number of sentences. Uh, it's pretty more difficult for sure. And and the second technology, uh, just just want to be sure if everything is fine. Just let me check about my mic, yeah, and screen. Yeah, everything seems fine. Okay, turn it to the full screen mode. And then the second technologies, yes, we stop it more or less here, called VAT polymerizations. So VAT, the vat or the tank or the tray. So something you use in order to store the polymeric material. So simply call the tank or the vat is fine. So the thing is that you have the polymer resin or, or monomers as the input materials. Yeah, and and here this polymer can be cured by using the light. That's why it's called photopolymerization resins. So the resins which made of polymeric material can be cured or can be cross-linked by under the influence of the light. So the light can be the UV light, or we call the ultraviolet light, or the how can I say, laser, or the laser can be the light source in order to irradiate onto the resin and to bond them together. In other words, to create a cross link between them and to make the physical object. And there are two configurations. You can see on the slide, there's upright configuration on the right side of the figure and the inverse configurations. So there is a certain difference between the two configurations, but it's easier to observe that with the upright configurations. If you see the building plate and the part will be grown up, yeah, with respect to the building plate, but to the how can I say, to the from the bottom to the top direction, let's say. From the bottom to the top directions, and once the printing is completed, and then the part is completely immersed in the resin tank, in the resin. Just mean that the building plate is continuously lowered the position, and once we complete the build, and then the part yes is submerged, is immersed in the resin, not in the water. And for the second configuration, we call inverse configuration. So is somehow opposite with respect to the upright configuration, where the path is grow, but the building direction is following the arrow, which is go from upper to lower, or from the top to the bottom. with respect to the building plate. With respect to the building plate. So you see the building plate as a reference, and how the part grow, or how the part build. Yes, will, how can I say, affect the way we call the technology. Yeah. And you see that the tray is quite small with respect to the upright configuration, and yes, uh, and once the printing is completed, and then the part is completely out of the resin. So this is quite commonly see in several technologies, several kind of machines like Form 2. Uh, these, how can I say, these the machines which are commercialized by Form Lab, is the company name, called Form Lab. Yeah. And during process, you see that there is an irradiation of the light to the cross section of the part where it need to be cross-linked, or to bond with respect to the building. How can I say, with respect to the previous layer, in order to create a 3D physical object. And after this process, you may need the post curing. So just remove the part from the building plate, or remove all type of supporting structures, and then polishing, and finally exposing the part again under the sunlight, more or less 24 hours, just to how can I say, just to improve the mechanical property of the part. So this is called post curing process. The initial curing process is to bond layer by layer, to create the layer, and to bond the creating layer with the previous layer. But then it's not well cross-linked, and therefore, in order to improve, if you want to improve mechanical properties of the part, and after printing process, it is necessary to, for some technology, it's necessary to expose the parts again under the sunlight. So that is support the post-curing process, and to obtain the how can I say, desired mechanical properties. So this type of machine, or this type of technologies require the presence of resin exposure system, because we need to irradiate the light. Can be the ultraviolet light or the laser. And here you have the SLA. SLA stand for the stereolithography, and CDLP. DLP is direct light processing. C is continuous and direct light processing. Yeah. Yes. And for the a little bit more detail about the two technologies, I'm sorry, two configurations of the polymerization. In terms of the upright configuration, you can see it here. So the building plate is go down according to the vector V2. So once the part is grown, and the building substrate is lowering the head with respect to the free surface of the resin. So the resin is refined after each build. To start the process, the building plate here, yeah, is positioned several hundred microns below the free surface of the resin tank. So the free surface is here. So just let the building plate lower it, and the head is exactly equal to the layer thickness that you need to kill by the light. You need to kill by the light. And the polymerization is done by irradiating the light to the area that needs to create the cross-linking. And once the scanning is completed for one layer, and the building substrate or the building plate will be lowered to the distance which is equal to the layer thickness. So it's repeated until we completely print out the 3D object. So one thing is that when you lower the position of the building substrate, and then the polymer outside will, how can I say, will flow to the free surface. Yes, because when you lower it, if it is water, seeing the water has low viscosity, độ nhớt, and then it's fastly flow to fill the free space, which is below the how can I say, the level, below the level of the free space of the resin tank. If it is water, but since this, in this case, we use the resin as the input material, and the resin typically has relatively high viscosity, độ nhớt, and therefore, when you lower the position of the building plate, it cannot fastly fill in the free space, and therefore you need time, you need to wait for a short period of time until the liquid resin filled completely to the area above the how can I say, polymerized layer. Polymerized layer, and mhm, and then you see that in order to form the uniform thickness of the resin, it takes times. So this is it takes longer time in order to fabricate the part. And now I will explain to you the inverse configuration. Configuration, because the inverse configuration is preferred. But since we have two hard surface, the bottom surface of the building substrate and the top surface of the bottom surface of the tank, and the two surface will come, and but they did not come into contact with each other. There will be a certain distance between the two, which is equal to the thickness of one layer. Is one layer. So let's say solid surface come together like this, but almost rich, and is easily, how can I say, creates the even layer of the resin material for the curing process. So it's faster. Comparing to the upright configuration. So on the next slide, we'll show you the working principles of the inverse configuration belong to the group of VAT polymerization. But let me open in full screen mode. And here we focus on the inverse configuration. And as I have talked to you for the inverse configuration, once the print is completed and then we have the part is out of the resin, So you see the moving direction of the building substrate goes up, and therefore once it's complete and is pulled out of the resin tank. I mean, the part is pulled out of the resin tank. Since we have the how can I say, the movement directions of the building substrate here, which is in opposite. Yes. So for each layer, I mean, the layer thickness is defined by the space or equal to the distance between, how can I say, the bottom surface of the tank and the below surface of the building substrate, at least for the first layer. But for the subsequent layer or for the next layer, it will be the distance between the bottom surface, the bottom surface of the layer, which have already been crewed, and the bottom surface of the tank. So they are two different things. So You have the space, the layer thickness is defined by the space between the building plate and the bottom surface of the VAT for the first layer, or the bottom surface of the tank and the previous Q layer for the subsequent layers. The path is projected upward, yes, because it depends on the moving direction of the building substrate here, so it goes up. The layer is completed, and the separation of the polymerized layer, yeah, to form solid surface is needed. So this, yeah, because this goes up, and then the resin is to how can I say, the resin will flow into the new space, yeah, in between the previous layer and the bottom surface of the tank. And then we have the irradiation of the light to the layer in order to cue this layer and to bond the layer with the previous one. The thing is that comparing to the first case, yeah, we just have the above surface of the plate and the free surface of the resin, and therefore you and for once each layer is completed and the plate is lowered at this position, and then you need to wait time for to allow the resin which located surrounding flow into the area between the cured layer and the free surface of the resin. But here in this case, you have in the inverse configuration, you have the two solid surfaces. One is the bottom surface of the tank, the other is the below surface of the building substrate or the previous cured layer. So the two solid surface. Yeah, two solid surface. So it's easier comparing to the upright configuration in order to form the even layer thickness for the curing process. In other words, you save time. You save time for forming and shaping each layer. You save time for forming and shaping each layer. And there are a number of materials that can be used for the inverse configuration. For example, elastic, yeah, polymer. I'm sorry, elastic polymer. Yeah. So normally we refer to the thermoplastic and thermosetting. Yeah, but here is elastic. I will check it. Elastomer, yeah, ceramic, elastomer like rubber, we call elastomer polymer. Ceramic composite, yes, magnetic, electronically and thermally functional material is quite general. Yes, there's no specific name about the material, but just group of material that can be used for the inverse configuration. But generally speaking, is preferable to use the polymeric material, especially the thermoplastic, yes, because it can be recycled. Okay, in Vietnamese, just to be sure that you understand what I have mentioned. Cho chúng ta có hai dạng configuration gọi vui là cấu hình, đúng không ạ? Dạng hướng lên trên và dạng đảo ngược. Thì đối với hai dạng này thì chúng ta sẽ tiến hành các cái phản ứng polymer hóa, đúng không ạ? Để mà polymer hóa những cái monomer ở trong cái thùng chứa, đúng không ạ, hoặc là trong cái dạng bình chứa VAT gọi là tank. Thế thì cái bình chứa của chúng ta sẽ chứa có thể là monomer, đúng không ạ, và monomer này sẽ được điền đầy sau mỗi một cái lần mà chúng ta tạo nên cái cross link, có nghĩa là khi mà các bạn tạo được một cái lớp layer, đúng không ạ, thì nó sẽ tự điền đầy lại sau mỗi một lần cái lớp đó được tạo thành. Rồi quá trình được bắt đầu như thế nào đối với cái anh upright configuration này, thì ở cái lớp vật liệu đầu tiên thì cái building plate, có nghĩa là cái tấm ở phía dưới cùng ấy, màu đen mà các bạn nhìn thấy ở trong hình vẽ, thì nó sẽ nằm cách cái mặt thoáng của cái bình chứa polymer một cái khoảng cách bằng cái chiều dày của cái lớp đầu tiên. Nhớ chưa? Sau khi cái khoảng cách đấy đã được định nghĩa bởi cái hệ thống định vị ở trong cái máy in, thì cái tia laser hoặc là tia UV tia cực tím nó sẽ được chiếu lên trên các cái lớp vật liệu mà cần phải tạo nên các cái liên kết bậc hai, đúng không ạ, để làm rắn nó. Nên nó sẽ scan qua những cái vùng đó, những cái vùng đấy là những cái vùng slicing mà được define bởi cái file STL mà tôi đã trao đổi với các bạn rồi. Chúng ta phải có 3 cái model trong không gian, đúng không ạ? Chúng ta phải chuyển hóa nó thành cái file STL, nó là dạng surface, dạng bề mặt, sau đó phải cắt thành từng cái cross section một, thì từng cái cross section nó sẽ define cái vùng mà cái tia laser hoặc ánh sáng nó sẽ scan qua để nó tạo thành từng cái lớp vật liệu. Đấy, và cái quá trình đó nó sẽ tiếp diễn cho đến khi nào cái model 3D của chúng ta được hoàn thành. Thế thì sau khi mà cái lớp vật liệu đầu tiên mà được tạo thành bởi cái việc scan tia laser hoặc là scan tia UV này, thì chúng ta sẽ tiến hành là hạ cái building platform này xuống một cái khoảng lại bằng đúng với cái layer thickness của cái lớp tiếp theo. Tại vì ở đây là chúng ta sẽ hạ, tức là ở cái bước thứ hai chúng ta đã hạ là 2 lần cái layer thickness rồi, đúng không ạ? Nhưng mà một cái layer thickness đã được tổng hợp, và cái layer thickness thứ hai thì chúng ta đang chuẩn bị tổng hợp bằng cái quá trình là scan cái laser qua cái lớp vật liệu đó. Thế mà có một cái vấn đề mà lưu ý các bạn là khi mà chúng ta hạ cái building plate này xuống một cái chiều dài hoặc là chiều cao bằng với độ dày của cái layer thickness, thì nếu như là nước thì nó sẽ tràn vào ngay cái khoảng không, đúng không ạ? Vì khi mà chúng ta hạ xuống thì lập tức nó sẽ tồn tại một khoảng không ngay tức thời tại cái thời điểm đó thôi, thì nước thì ngay lập tức nó sẽ tràn vào. Nhưng mà đối với những cái chất lỏng mà có độ nhớt cao như là monomer resin này chẳng hạn, thì nó sẽ rất từ điền vào, bởi vì là chúng ta biết là cái dòng chảy của nó sẽ là dòng của các cái lớp chất lỏng, đúng không ạ? Và giữa các cái lớp đó thì nó sẽ có cái sự ma sát, và những cái anh có viscosity này càng lớn thì cái ma sát nó cũng càng lớn, mà nó làm cho cái quá trình chảy nó rất là chậm. Như vậy là để mà cái polymer ở những cái vùng xung quanh nó điền đầy vào cái khoảng không đó thì chúng ta cần phải chờ một cái thời gian, bởi vì ở đây nó chỉ đơn thuần là trọng lực để nó kéo cái lớp vật liệu đi vào cái chỗ mặt thoáng đấy thôi, để điền một cái lớp vật liệu tiếp theo chuẩn bị cho quá trình scanning process. Thế còn đối với cái anh inverse configuration thì chúng ta thấy rằng là gì, lúc này là cái vector di chuyển của cái building plate nó hướng lên trên, cho nên là sau khi quá trình in hoàn thành thì cái vật của chúng ta kéo ra khỏi cái bình chứa polymer, kéo ra khỏi bình chứa polymer và không được nhúng ở trong cái bình polymer đó. Thế thì mỗi một cái layer thì nó sẽ được define cái thickness bởi cái khoảng cách giữa cái mặt dưới của cái building substrate và cái mặt trên của cái đáy của cái bình chứa, trên của đáy bình chứa, đúng không ạ? Thì ở cái lớp vật liệu đầu tiên ấy thì rõ ràng là khoảng cách giữa cái mặt đáy của cái building plate này và cái bottom surface nó sẽ chính bằng cái thickness của cái layer đầu tiên. Thế thì sau khi cái layer đầu tiên nó đã được định nghĩa như vậy thì rõ ràng các bạn chỉ cần sử dụng nguồn sáng để chúng ta scan qua cái vùng mà đã được định nghĩa bởi các cái slide, đúng không ạ? Nó quét qua để nó cue tạo ra các cross link giữa các cái mạch polymer của chúng ta và làm cho cái polymer chúng ta rắn lại. Và cái quá trình đó thì nó cứ tiếp diễn từng layer một, và layer thứ hai thì đúng không ạ, thì cái vector thì cái building plate này nó sẽ di chuyển lên phía trên đúng một khoảng cách bằng cái chiều dày của một cái lớp vật liệu, và cái quá trình nó sẽ tiếp diễn cho đến khi mà cái model 3D của các bạn hoàn thành. Đây là physical object, đúng không ạ? Thì cái hệ thống của chúng ta thì bao giờ cũng sẽ gồm là cái bình chứa polymer, đúng không ạ? Cái sự di chuyển của cái building substrate mà có gắn liền với cả 3D object, và cái exposure system để các bạn tiến hành scan light cho cái quá trình polymer hóa. Thế thì ở đây nếu đem so sánh với cả cái upright configuration thì chúng ta có hai cái bề mặt cứng là bề mặt đáy của cái anh building plate và cái bề mặt dưới cùng ấy, mặt đáy của cái anh bình chứa. Thì khi hai cái anh đó nó tiếp xúc gần lại với nhau thì nó sẽ dễ dàng trong cái vấn đề là tạo ra một cái bề dày uniform, có nghĩa là đồng nhất, đúng không ạ? Tạo bề dày đồng nhất để mà tiến hành quá trình scan cái ánh sáng để cue cái lớp vật liệu đó. Và cái quá trình này ấy, nếu mà đem so sánh với cái anh upright configuration thì nó diễn ra nhanh hơn so với cả anh upright configuration, vì các bạn biết là đúng không ạ, chúng ta có gravity, cái trọng lực nó tác dụng vào, nó sẽ kéo cái lớp vật liệu ở dưới đáy, nó điền đầy khoảng không này nhanh hơn so với cả cái anh mặt thoáng ở phía trên. Và ở đây chúng ta sẽ có hai mặt đúng không ạ, chúng ta ép nó xuống đúng không ạ, đương nhiên là nó sẽ phải tạo thành một cái hình lớp vật liệu nhanh hơn là so với cái anh là chỉ có một cái mặt cứng và một mặt thoáng. Rồi, đây về configuration, về cái file ở đây tôi cũng có thể show cho các bạn luôn. Và trong quá trình show, tất nhiên là tôi biết là các bạn có thể xem được ở nhà. Tuy nhiên là trong cái quá trình mà tôi trình chiếu như thế này thì tôi cũng có đưa ra một vài các cái discussion liên quan đến cái video clip mà tôi tìm và để trình chiếu cho các bạn. Stop sharing. And then I'm trying to open the come on. SLA. Okay. Here. Where is it? Here. Okay. So how SLA works? So as I already mentioned to you, Formlab is quite a famous company in supplying the 3D printer machines based on the VAT polymerization, and this is the inverse configurations. And after the printing process, yeah, you see the refilling, yeah. The polymeric material is deposited onto the tray firstly, and during the first working cycles, we have the layer thickness definition by the two surface. One is the bottom surface of the being substrate, and the other is the bottom surface of the tank. Yeah. And once the thickness is defined, and then the laser will be irradiated onto the layer in order to kill the polymeric material. Yeah, the laser irradiated or the UV light. It's quite fast, but in the real condition is not as fast as you see because for example, for one motor which have a centimeter in height, it takes around 10 or more than 10 hours. So what you have seen is the how can I say, the speed of process is not the real process. Yeah. Okay. So the building substrate move upward, and once the 3D printing is completed, and then you have the part which is out of the tank, which store the resin. So simply defining the layer thickness, yeah, and afterward you the system will irradiate the laser or the UV light in order to cure the layer materials, and finally we how can I say, move the building substrate in order to continue the process with the upcoming layers. So that's the thing. Sorry for a minute. Yeah, so let me continue with the next slide. I think that I have already turned off the PowerPoint. Let's see. Where is it? Okay. So the third AM technologies that I would like to highlight during the course called material setting, and you can have an overview of seven technologies here, where we have the material extrusion and the VAT polymerization, material setting, sheet laminations is not commonly used. Yeah, we have the technologies, but I rarely see. Yeah, but this is my case. The powder bed fusion is quite famous. Is quite popular in order to print out the metallic material, the metallic part. By the setting, it somehow combined the powder bed fusion and kind of material setting, kind of, kind of. And finally, is the DED technology called the direct energy deposition. Is something like the 3D printing process, which is somehow related to the robotic arm, and is usually it's how can I say, deposit material directly to the position where we need to build the part. So comparing to the powder bed fusion, is can this technology is more flexible in creating the larger part. Yeah, but of course everything has two side effect. And since it can be used to build up the larger part, and the accuracy is lower comparing to the powder bed fusion. Okay, let me come back with the material setting. Material setting is a technology that can be used in order to form the part by using, again, the layer, by using, how can I say, to form the layer by using a single or arrays of nozzle. Single nozzle, or the combination of different nozzle, yeah, aim at depositing the droplet of material, droplet of material on the surface. So once the deposition is completed, and then for each layer, the curing process will be performed in order to cure the material. And curing it just somehow like a polymerization is meant to create the cross link or the bond between the how can I say, material, tạo cái sự liên kết, cue, tạo cái sự liên kết giữa vật liệu. So the material setting can be used to print out different kinds of materials. For example, the hard plastic material, rubbery, yeah, cao su. This technology can offer higher scalability in productivities. Can scale the part dimensions. So for sure, for example, if you design the part with the head of centimeters, but now you do not want to print it out with the centimeter head, and then you can scale down 50%, yeah, and print out the part, yes, with, for example, with the head of 5 centimeters, just for visualizing the part. Because you see that one of the purposes of using AM technology is to create prototype. So it's not for creating the part subject to work, but it can also be used in order to fabricate the part just for visualization, just to show your boss how the part looks like. And yes, and in that case, is the materials I think can help offer higher scalability in productivity, and material flexibility. So these offer the wide range of material to be printed out by the material setting. And typical commercial system can have 15 nozzle, yeah, or more. Yeah, 15 nozzle. So you can deposit more material, which can help you to improve the productivities of the process. Yeah, uh, comparing to the single nozzle. So yeah, deposit, yeah, droplet by droplet, line by line, layer by layer. So it take longer time for single nozzle. But if you use the arrays of nozzle, so two line, for example, three line of a nozzle, and in each line you have, let's say, 10 nozzle, for example, you have an array, yeah, and then it will absolutely increase the productivities of the process. Yeah. And we have a wide range of materials, yes, but is somehow noted above at plastic material rubbery. Yes, so a little bit more detail, we have photopolymer. So this means that the polymer that can be cured by photo, by light, wax, conductive ink, so on. And here, if you see the figure on the right side, so you have two kinds of material that can be deposited here. The first is support material, and the other is the material of the part. One is the highlight by the white color, and the other is yellow color. Yeah. Now we have the on the setting head. This is equipped with multiple nozzles. Yeah, multiple nozzle or arrays of nozzles that can be used to deposit the plastic materials, both the part material and the support material as well. And once the deposition is once the head it goes through a certain area, and then the UV light is irradiate onto this area in order to cure the material. And for the figure, which is located at the bottom of the slide, is maybe easier for you to see that you have a two input material, yeah, photopolymer material and support material, yeah. And you also see the nozzle here. It's just the representations of the configuration where it's shown only two, but in fact, yeah, it can be much more than that, many more than that. It can be many more than that. Yeah. Yes. And I can show you the video. Oh, come on. Advertisement. But I mean, come on. Yeah. One window. What is that? Here. So it can be in full screen, but I just let it like this because it's not necessary. So you can see the head, which is equipped with multiple nozzle. Yeah. So it's deposit the material in droplet, and then directly afterward, it can be cured with the UV light or the laser. So it's like the printing process. It's, yeah, because it's the 3D printing. Yes, it's like a printing process on the paper, but it's not the case. So you have motor in STL file, yeah, and it needs to be sliced, yeah. And for each slice, you define the cross sections or the area that the laser or the light will be scanned through. So just defining the boundary or the area or the restricted area that the laser or the light will scan through, and the material will be deposited onto as well. So multiple nozzle, deposit the droplet, yeah. And the process is repeated until the 3D physical part is formed. Yeah. And then when it's completed, you need to remove the part from the building substrate to polish the surface, yeah, to make it smoother. Yeah, it's the post-processing to make it more attractive to your customer. And yeah, it's quite great. Let's think about the fact that, okay, you need to stop on production line in order to fabricate just a prototype to show your boss. But here, you just have a printer to create the prototype or whatever you want. during the product development process or even for the final product. So this is quite fine. This is quite fine comparing to the case of the how can I say, the shutdown of the whole production line. So it's not reasonable. It's not reasonable. Stop. Yeah. And yeah, here material setting technologies. And yeah, the technologies that I have been talked, that you have been talked, is the sheet lamination. So generally speaking, yeah, I do not see it very frequently, but it's still one of the how can I say, AM printing technologies that are available at the moment on the market. So basically, you it's something like you create a paper, something. Just image that you have a paper, and now you have another paper, and you need to use the adhesive, the glue, for example, in order to bind the previous paper with an upcoming paper with the next paper, and the process happen. Yes, so you have the yeah, have the physical part which made of multiple paper. Yeah. But if you need to create a little bit more complex shaped part, so just form the paper first. Yeah, just by cutting, for example, laser cutting or another type of cutting, and then attach them together or bonding them together, and then you have the final 3D physical object. So this is the idea of this technology, sheet laminations. Yeah. The process is that you bond the different sheet of materials, and this material can be the polymeric material, can be metal. But for metal, you have the wetting process in order to connect different thin wall structure. Let's say thin layer metallic materials, or it can be composite. And the bonding process can be handled can be handled by applying heat or pressure, or both heat and pressure. Yeah. And finally, you can cut the material, stack to desired contour of a given layer. Or maybe you can cut it first and then bonding them together. Yeah, it depends. Composite system, you can apply heat and pressure or both, yeah, to chemically or mechanically bond the sheets together. Uh, yes, because you apply the force by using the roller, a Lun F, yeah, and together with mechanical cutting and laser cutting. And there is a company called Fabriconic commercialize the metal sheet lamination. Yes, let's say machine or technologies. So they wet the sheets of metal together ultrasonically. In this case, because we wet together metallic materials, so there's no need to use the adhesive. Yeah, is a wetting process. Yeah, to stack. How can I say, to attack them together and bonding them together. Mhm. And finally, they use mechanical milling in order to shape these layers of materials. Search for a minute. Sorry. It's long, just for fun. It's a long process in order to nourish uh, children. Let's say. So once your daughter fever has been completed, and then the fever of my son is coming. And then, oh, okay. So Yeah, as I already mentioned, for the metal sheet laminations, so different kind of metallic sheet can be joined together by the welding process. And in this case, yes, people use the ultrasonic, I guess, and the mechanical, how can I say, uh, mechanical activated also, in order to bond them together. You have the heat, you have the ultrasound induced diffusion. So the bonding process here is at the high temperatures, and then the atom is provided by the energies, and it can diffuse between different layer between different layers in order to bond these layer together. So this is the idea. Yeah, and once the bonding process has been completed, and then people can shape the geometric feature of the layers, by cutting like mechanical millings. Yeah. And I would say that is nothing special. But I rarely observe these technologies in practice. For sure, is available on the market, but I rarely see in my situation. So the idea is not new. The idea is not new. The technologies may not be new, but it can be categorized as one of the seven technologies for AM. Yeah, so just group it here, and let's try to show you the stuff here. I can share. Yeah, advertisement. Yeah, you have the Fabrisonic company that generate this kind of machines to wet the sheet metal together. So it's formed layer by layer, and then yes, for sure, it's categorized as metal additive manufacturing. So you see the attachment between different the attachment of different layers material. Yeah, is the bonded part, and then we need to cut the residual material. The idea is not new, I would say. Okay, I think that we can stop for a while, let's say 10 minutes, and afterward we can continue with the next slides. And just remember that between 2:30 and 3, yeah, please type your name, yeah, for checking attendance.